some kind of emails from those communication group. I sent an email and nobody responded. So then I said, what do I need to do? So when I was preparing class yesterday, and I was thinking, okay, it's matter. Maybe I just invent some problem for you guys. I look at your homework due on this incoming Friday, so I will have that homework. Similar problems will show up after I'm done with this. Okay, so just remind you, we are on this particular example, which is a toy car pushed against spring like this, and then the first question is how fast it is going before going up the ramp. In other words, this toy car pushed against spring at one particular instant. So the idea, I usually prefer to show you the step-by-step fashion. How do we calculate this one? So I'm going to show you a step-by-step fashion like this. So step number one, what we need to do is that we need to identify which one is initial, which one is the final stage. So in other words, identify the initial and final condition. So which one is the initial and the final step? I should say step, but nevertheless, just use a condition. So if you read the problem, you will notice that the initial clearly is compressed on the spring. But the final, watch carefully, this is very tricky in this case. It only says how fast it is going before it's going up. In other words, before this car goes upward, this is our current final position. So let me use not a situation. Let me use a position instead of a. Could you guys change this to position? So this one is very important in the sense that if we identify what is the final, what's initial is very important. For our problem currently, our initial condition is going to be, that initial condition is going to be compressed the spring. So in other words, the car doesn't move, it just compress the spring. That's it. And my final ones, right there, Will. Final ones here, let's go to final, will be the uncompressed spring and the car is moving before it goes up the ramp. So these are the initial and the final positions. Okay. For those of you who understand this, could you show me card A, please? If you understand this stuff. This is a very important step. Show me your card A. If you understand this one, show me card A. All right, everyone's card A. Yeah, make sure you do show me card A. Excellent. Wonderful. Yeah, thank you. Especially those of you in the back, I really want to show card A. So this is the first step you need to identify. So then here I have the mechanical energy. I will write a ME. And I will write a MEF. That's the mechanical energy initial and the final. So that's step number one. Step number two, so the conservation of mechanical energy. So we're using the conservation law of mechanical energy such a way we want to calculate them. So the conservation means my initial mechanical energy equals my final mechanical energy. So that's what we have. Did you see we have an initial condition like this, the compressed? So therefore we're going to write out what this ME is going to be. Because we have a spring, so therefore it must have spring potential energy. So in our class we use SP. That's initial, the potential energy from spring, so spring potential energy. And of course, besides spring potential energy, what else we would like to add? Potential energy, and the other one is kinetic energy. Good job. So, and the other one is the kinetic energy. So that's what's called mechanical energy. Now, the compressed spring potential energy is 1/2 kx squared. That's the potential energy. Always this expression. Now, how large is the kinetic energy of the car? I press. Does the car move? Does the car move? No. So therefore, how large is the kinetic energy? It is going to be 0, of course. This is going to be 0. So it's not move at all. And the final ones, I do the same thing. So you see now, the spring is not compressed anymore. So therefore, the potential energy of this guy is going to be 0. So whether any doubt, it is x equals 0. So that's why everything equals 0. Now cars are moving, so this time it has kinetic energy. Vf squared. Okay. Just keep in mind, this initial, this final, just pretends to be this part. It's not universal. It's not a universal. It's just for this particular part A, I will say this is initial, this is the final. I cannot use it for the latter steps. Now the conservation means these two is going to equal to each other, so this will equal that. So then what I have is 1/2 kx squared equals 1/2 mdf squared. Okay. And this is the conservation of mechanical energy which we use. Now let's see whether we are able to calculate this already. Do we know the spring constant? Yes or no? Yes or no? Yes. So this is good. What about x? Yes or no? Do we know the compression? How much compressed?
Yes.
Yes. Good job. Do we know the mass?
Yes.
Are we able to calculate velocity?
Yes.
Let's do it. 2 minutes calculation. Cf. Yeah, make sure everybody should do it, and then you can compare your results with your neighbors. Okay. Yeah, make sure you do compare your results with your neighbors. Those behind you, on the left, on the right, front. I want everybody to do it, not just the 1 or 2 students do it. I want everybody. When you got the results, you check with your neighbors, see whether your results is good. Where is my seat? Oh, you have to check it? If you see, sorry, your class full. Don't worry, you know about the seat right? Yeah. Let's go all the way. Check with your neighbors, see whether your results is good. All right? I want everybody to do it. Check with them. Compare with your neighbors. So that way you will have a better understanding how this works. Anyone already finished? Could you raise your hand, please? A little bit higher. Okay. Cool. How loud do you guys get?
What?
How loud do you guys be? Okay, good. Get this? Did you get this? Okay. Did you get it? Okay, wonderful. Let's wait 1 more minute and make sure you are able to do it. Yeah. Okay. Check the results. Make sure you figure it out and check with your neighbors. Check with your neighbors. If you have a question, just raise your hand. I will be more than happy to help you. All right, that looks good. So, did you guys get 2 meters per second? Like this? Okay, if you do, could you raise your hand if you got the same answers from this? Okay, good. Anyone want me to show you how we do it? Anyone want me to show? Okay, one student. I'm going to show you how we do that. Did you see we have 1/2 here? Did you see what I do? Both sides cancels out. And then our spring constant here, K, equals 250. So that would be 250 times the compression is over 4 centimeters. So this will 4 centimeters, 0.04 meter. Oh, 4 meters. Yeah. All right. 4 squared. So that's what we have. Yeah. So that's 4 centimeter, and the mass equals 0.1 kilogram NV squared. So that's all you need to do the calculation. So I think this should be straightforward. Yeah, this is the correct answer. Okay, any question on this part? All right. Let's move on to the next. Okay, so all right, let's see what we have next. The next part of the question is the follows. Yes. All right, and here's a question. It says that how fast it is going after going up the ramp. In other words, here's the starting point now, the ending point here. Did you see 18 centimeters? Did you see 18 centimeters? In other words, which one is our final state? Which one final position? Should be what? Should be here, right? Makes sense? Should be here. In other words, you see, our recipe still works. And I will keep everything as it is. And you're going to see me, I'm going to repeatedly use this particular information. So what I will do, this time, the spring is uncompressed. So I'm going to write this down. So all I need to do is change uncompressed. That's simple enough because it's not my final position. So this final spring is also not compressed. And now here the car is moving. Here's the car moving. Makes sense because that's after the compressed. The initial car is moving, the spring is uncompressed. The final step is also car moving. So that's what we have. Now this time we're going to show you the second step. So essentially, we're going to use all these similar equations that we did before. So the first step, let me move my camera this side, so it's easier to see them. So all I need to do now, I'm going to rewrite everything as we did it before. So I'm going to erase this one now. So the spring potential energy this time is going to be 0. But there's one extra term will play the role. What the extra term? Besides spring potential energy, what the others? We elevate it. Remember, we elevate. What will increase? A word start with a G. GP. Make sense? Gravitational potential energy increase. In other words, originally we have this expression because now you have elevation change. So you're going to have a GPE. Because if there's no elevation change, you just delete them. It doesn't matter because it's the same reference point. But now we add another extra terms here. Once we add another extra term, here is also SPF, GPE final, KE final like this. Did you see the knowledge you gained is very little? In the sense that only the elevation adds this extra potential energy there. As potential energy, that's what you get. Okay, if you understand this step, could you show me card A, please? All right. Anybody still have questions? Yes, question.
One particular question is how do we end up using gravity potential energy into this equation?
Great question. I'm going to write the answer on the board directly, so that way I just not say it. The reason why we immediately inject that is because there is a change in height. There's change in height. Go ahead.
So are we dividing the spring potential energy by the gravitational potential energy?
Sorry?
Are we dividing the spring potential energy?
No. There's extra term added into it. Extra term.
So it's spring potential energy.
And the gravitation. Exactly. So this essentially will have an extra term added toward the potential energy. So initially you will have spin potential energy because gravitational potential never changes on level ground. Essentially just move like doesn't matter. So you see here doesn't matter. So here's the gravitational potential energy is, if you include it, it's the exact same. It doesn't make any difference. But now you see the elevation change. You see it. So this is elevated about. So that's all you drop down, then the gravitational potential energy is going to play a role. You could actually add this gravitational potential energy in the first place. But then it makes no sense because here's the add zero, another add zero, so there's no big difference. That makes sense to you? Okay. Any other questions? Any other questions? Okay. That's very important. So essentially, if there's no change in the height, you can simply ignore the gravitational potential energy. Just that. It's the same way if there's no compressed. It's uncompressed. You can ignore the spin potential energy because there is no potential energy involved. So uncompressed, you can remove these guys completely. In fact, this equation is excessive. These two terms are all zero, so you do not need to add them. In the beginning, if I add them, you will see you have 3 terms, Dr. Zhang, I'm good, overwhelmed, right? But now you add a little further, it's not that extra different. So that's the key. Now, all we need to do, we're going to put this guy to 0, because it's not compressed. Put this guy to 0, it's not compressed. So that's all I need to do. Now I need to figure out how large the gravitational potential energy, this initial ones. So this one here will be extra information which is added for you guys to see here. And this step, I'm going to call it step 2.1. This extra step point into it. This is called set 0 potential energy point. If there's no gravitational potential energy involved, you do not need to do this. But now we have to do it because you have the elevation difference. So then you and I have to agree which one is your 0 potential energy point. For me, I would prefer set this guy equals 0. So that makes things simpler. Then everything will be referenced to that particular point, which is the original, the horizontal line here. So this is my reference point. So then you see I have a y here. So this my y becomes the step 2.1, 2.2, forgive me. My final position is going to be the edge now. So this edge itself, let's take a look at this. Edge itself is 18 centimeter. So this will be 18 centimeter. We convert to meters. So that is my final position, the height. All right. So in other words, for the second part, I will only need to do these two, but you do need to set which one is your reference point. Of course, final result is the same, but you have to set it. Since we decide this one is to 0, so this will be 0, like this. So this essentially will be 0. And now, this one here, we will figure out how large GPE final. GPE final is mgyf. So that's the potential energy equation. And we know the mass, so let's add this mass here. So this is the mass, will be at 0.1. And G is 9.8. And then we'll multiply by Y, which is final. So this you have a value like that. So now, so in other words, this term is known basically. Do we know KEI? Do we know KEI, initial kinetic energy? We know that? Do we know? Yes or no?
Yes.
Yes. In other words, we can calculate. So this KEI just equals 1/2 mvi squared. Now this initial is really, once it leaves the spring, and that's how large this one. We also know that. That's the 1/2. We know the mass 0.1. And the velocity, we know that's 2 meters squared. Okay. Are we good so far? We so far so good? Okay. Could you guys show me letter A, if you understand it? Otherwise, show me letter B. Otherwise, show me letter B. Okay. Good. All right. Thank you. Yeah, if you still have questions, please let me know. So now all we have is essentially ME equals FE. So we know this. We just calculate like that. So we know this, so we just got that. And this is 0. So essentially you will see, essentially this number, whatever you calculate, is going to equal KEF plus GPEF. Does that make sense to you? And you can find out the velocity like this. And this step, last step, I'm going to write on the top here. Step 2.4, I'm going to summarize this step for you. Otherwise, the equation is a little bit too long. I want to summarize it. So that way you will see better here. So again, I'm going to summarize it. So the summary is the following. My left-hand side is just KE initial, because these two are zeros. My right-hand side, I have GPE final plus KEF final. And then, folks, let's calculate this time how large the new final velocity is going to be. I'll give you 3 minutes to do the calculation. I'm going to count it right now. That right now is 32. I will check you guys 35. If you have questions when I walk around, please stop me so I'll be able to answer any question you may have. Just show the diagram here would be very good for the students see them. Okay, very good. 3 minutes. Working on that. If you have a question, just raise your hand. Check with your neighbors. Check with your neighbors. You will get KEI from this equation. Good. So you got this number, you're going to find it here. All right. True, yeah, you got this. You get a number. Right? Okay, there you go. Just write it down. And then G. This is this equation here. And plus, no, technically, what we're looking for is you're going to find it. Make sure I said it. So, you can find it. And then once you calculate that, then you can find the velocity, right? Because the big energy 1/2 mv squared, the whole thing is equal to 2 squared over 2 equal that number, whatever you got, and all you divide by n both sides times 2. That's it. Okay, yeah, sure. I can write an equation on board. How about that? Sure, I can do that. I will write over here. How about that? Is that helpful?
Perfect,
Okay, yeah.
thank you.
Okay, that's all 3 equations you play with though. No more than this you need to learn. Okay, you're welcome, no problem. Any other questions? Any questions when I walk around? Yes, questions? Anyone? Yes. Check with each other. Check with each other. Did you guys have savers?
I'm about to have a slightly.
You guys savers?
So that's
Okay, really good, please. Okay, so that's good. You get same results? Same results, check with your neighbors. Same with this. Move over there, check with them. Make sure you are going to check with your neighbors, see whether you got the same results. Okay, check with your neighbors, check with your neighbors, check with your neighbors. That's how we learn the things. Yeah, get out there, walk around. You check with other folks. How long do you got? I don't know what it is. I haven't calculated either, so I don't know yet. Okay, all right. Okay. Okay, the important thing is you need to do it, all right? Folks, I will leave this box here. I won't remove whatever, just keep this here. That's the most important box. If you want to get bigger, that's great. Yeah. So that's very important. So we're going to do a little calculation here. How large the KI, you guys got? How large the KI? Just this number, how large?
0.2.
It's 2.2, right? This is 0.2 joules. So in other words, I'm going to write this down. This is 0.2 GPF. How large this one is? How large is this? 0.176. Okay. Anyone else can confirm 0.176? Okay, very good. So my KF. So then my KF just equals 0.024. Is it 0.024? Is this correct? Should be correct. Yeah, it should be correct. Did you guys get, is this correct? K final? You get it same? Okay, very good. All right. How many of us got the same kinetic energy final? Could you raise your hand, please? How many of you got different results from this? Okay, how large you got?
It's 0.0236, but the only reason it's different is because she rounded the...
Oh, she rounded up for this number, is that what you're saying? Oh, okay. Okay, so, but it's comparable to this number, what you get, right? Okay. All right, so, yeah, it could be a round up. All right. So, but at least most of you agree. Yes, go ahead.
I do not see that at all. How would we get to that part at all?
Okay, sure. Let me use my calculator. I just want to verify it. Are you being able to get KI 0.2? Yes or no?
I don't think I've gone to that part yet.
Let me show you here. How do we get this 0.2? This is the 1/2. 0.1. Now 2 squared is 4, right?
Right.
So then this gives you 0.2. So you see, 0.1 times 4, 0.4 divided by 2, you get 0.2, 0.2.
There's that. And then once I go into the equation right there.
Let's look at this one for just give me a second. Let's look at this one, how large this one you got. Let me type it. So I'm using this equation now. 0.1 times 9.8 times 0.18. So I will get 0.1764. Could you check? Did you get the same number?
I got the same number.
Good. So I'm going to add this 4 here. Now I'm going to do both sides minus this number. So I will both sides minus this number. 764 minus plus 0.2. So I will get 0.0236. Did you get this number?
Now I figured that.
You got it? You got it out. Okay, very good.
Yeah, because apparently I divided it.
Oh, that makes a lot of sense. Okay. Anyone has any other questions? questions? I just want to make sure everybody on the same page, because it doesn't make any sense if I just run over too quickly on this.
We're supposed to solve for velocity.
Yes, we are all the way to that. Yeah, we're not there yet. So now, in order to calculate the velocity, what we use this equation to calculate the velocity. So all we need to do, we're going to plug this guy back into this equation. So, sorry, the board is a little too small. We should a little border. So can I erase this part? I'm going to erase this part a little bit so that way you can see it. So what I have, my k equals this amount, 0.0236 equals 1/2. And I believe my mass is 0.1, and the velocity squared like this. So all I need to just both sides times 2. Both sides times 2, so this half cancels out. What I need to do with this 0.1, both sides divide by or times 0.1. Should be divide by 0.1, right? So this would be divide by 0.1. Divide by 0.1, so then you see 0.1 cancels out. Are we good on this step? Can you guys show me letter A? I just want to verify. This is the most important step. I want everybody got an A, all right? So that's why you show me your A. Wonderful. Good job, good job. Let's move on. So I'm going to do the times 2, divide by 0.1. So I will get 0.472 equals B squared. What I need to do next? Square root of both sides. Great job. Square root of both sides. So I will take square root of both sides, and I would get V equals 0.687, and I have a little more suffix afterwards. So this is my final answer. How many of us got the same answer? Show me your A letter. Show me your A letter. I love to hear that. Okay, well, not too many, but it's okay. That's fine. So you guys understand how we do the calculation, right? Okay. Questions? Any questions? Any questions? Yes, go ahead.
How do you get the 0.0236?
How do I get this guy's here, 236? You know, how do I get this one here? What I did was, on both sides, what's capital, minus this one here, minus 0.176. So this way it cancels out. Mm-hmm. So I have 0.2 minus this number, so I get this number out. Make sense?
Okay, yeah.
That's how I did it. That's how I did it. Okay. All right, I hope you guys follow me. All right. This is a video tip in case if you need to watch millions of times, you can too. So it should be good. I think it's camera. Oh, sorry, my camera aimed in the wrong direction. But anyway, I will video tip all of the things here. So that's what you're going to see the entire expression like this. Okay. And this is the part, second part, and the one last part. And how would this world change if it took the alternative path? Would it be final velocity be different if it changed different paths? Yes or no? There will be absolutely no difference. Because the final mechanical energy and initial mechanical energy, they are exactly the same, so there is no change. The answer should be no. All right? Anything else? So that's what his lecture notes about. So this is the thing that you will see that. So you see 469. Did I say 469? Yeah. Yes, you see 469. So his results and my results are completely consistent. Oh, I didn't expect to run so quick, so long. Folks, I'm going to show you one of the very important examples, and I want to show you here. Just give me a second. This is going to help you guys for the homework. I will show you here. This is the. Could you guys write this down, please? This is going to be, I'm going to need this. I want to go to the homework, please. So this is the homework, which is I'm going to maximize it. I probably won't be able to completely cover that. So this is the homework problem. I won't give you some hints on board such a way that you will have a better understanding how do we solve for this. This problem, when you work out that, it takes a little bit effort to do that, but not a terrible bit. So here's the solution. How do you do that? You will see that there's a spring. It's spring number 1. Here's a spring. It's called K1. And here's a block. It's called N. There's another spring which is over here. That's K2, like this. So this is a problem. And the distance between these two ends is a D. Is a D. I think they could use a D0 again. They use a D0. The first question it asks you, part A is ask you what's the if I compress this and then release it, how much compression will be on the K2? In this case, my initial position will be here. You guys write this down. This initial position, and this is the final position. That's what you will have. So all you need is you're going to use the mechanical energy conservation, and these two are equal to each other. So your final expression, and for that one, you will end up with 1 K1x1 equals K2x2 squared. So this is the equation you're going to end up with for the part A. For the part B, it's calculating the velocity. So I'm going to use a blue pen to show you what you will get. So your initial position is here, and the final position is over here. So then what you will end up with, you're going to have the equation look like this. It's going to be 1/2 K1x squared, 1/2 MBF squared. So that's my second question. And then the last question you need is the part C. Part C, about 1 minute. The part C, the final equation with mu k mg d0. This is the work done by non-conservative force equals the kinetic energy of the kinetic energy is 1/2 k x squared minus 1/2 k1 x squared, like this. I will plan to post the entire solution as an example. Could you guys take a picture of the problem itself so you can see my numbers? And I will scan this copy and I'll post under my OneNote drive, so that way everybody has it. If you have any extra difficulties, solve the homework problem, please do let me know. I can even create a video like what I'm doing here. Sounds good? I just try to see whether this will be helpful. Hope it's helpful. All right, good. See you guys on Friday. You make sure you take a picture like that.